snapshots of what happens in trying to reconstruct images. Now this picture here is a snapshot of a bullet traveling through an apple. And this is a famous photograph because at the time flash photography was still being developed, and this was at the time one of the fastest flashes that was available, which is microseconds in duration. Well, it turns out that we can do better nowadays using very fast lasers. But the idea associated with this picture here is that you have a pump in the system, which is the trigger for the gun that's going, so the bullet's going, it starts the bullet traveling. And then we can choose at which point we want to take the picture. So if we take the picture early, then the bullet's still coming towards the apple. And then if we take it a bit later, we can see that it's just starting to hit. And then we can actually take pictures as the bullet's traveling through. And we can build up a movie of what's happening. Well, the advantage of doing it like this, where we take a bunch of separate images, is that it allows us to capture behavior that's much, much faster than what we can get with conventional video cameras. And we can actually use fast lasers, and we can capture dynamics on 100 femtosecond timescales. So this is 1 × 10⁻13 seconds. So it's on extraordinarily fast timescales. For comparison, conventional video cameras have something like 60 frames a second. And so some of the things that you can see with these kinds of techniques are, with hard drive technologies, for example, we're interested in how bits flip on really fast timescales, because you want your hard drive to operate reliably and you want it to operate very quickly. So if you take a bar magnet that's originally magnetized in this direction here and apply a magnetic field in the opposite direction, the idea is that you want it to switch from this direction to this direction. And the question is, how does that happen? Well, if you just apply a reversal magnetic field in the opposite direction, it starts to reverse at the ends here, and then it breaks down into a bunch of little domains, and it reverses in pieces. And that process takes about 2 nanoseconds to occur. If you apply a little bit of a magnetic field in this direction here while you apply the reversal field, then the whole bar magnet reverses from this direction to this direction as a whole. It still reverses a little bit quicker at the ends, but it reverses most of the way as a unit. And the reversal process is mostly finished in less than a nanosecond in this case. So techniques like this let us really see and get insight to what's happening on very fast timescales. And we can construct movies of what's going on. We can also use time-resolved techniques with X-ray sources for the imaging, and this allows us to have better spatial resolution in our structures. So if we have a little strip line here and our little magnetic sample sitting on top of this waveguide here, we put a current pulse through that wire. That gives us a little magnetic field around the wire, and that excites the sample. So the magnetic field looks like this in time. And then we look at the sample by shining X-rays on it and collecting the electrons that come off of it. And these X-rays are pulsed, and that has about a 90 picosecond duration for the pulse. So 90 times 10 to the minus 12 seconds. And we can shift that. We can shift our camera flash when we're looking at our samples with respect to when we're triggering the event, which is our magnetic field pulse here, and we can build up a movie. So this is a vortex, and what you can see if you look really closely at this central area is that central area is wiggling around as a function of time, and that happens at a very specific frequency. So we can look at the dynamic modes that are associated with these little tiny structures and how they move around on really small length scales and really fast time scales. And a lot of times that gives us insight into what kinds of things we can use these for in the future. So I'll sum up now. What I hope you've taken away from this is that we have all sorts of amazing technologies that allow us to create and to see nanoparticles on very small length scales and very fast time scales, and that we have great capacity for studying magnetic materials on these time and length scales. Nanomaterials, nanomagnets in particular, are already a part of our everyday lives, and they have great potential for many future technologies, including new medical technologies, new devices for storing and for processing information, and for communications technologies, as well as all sorts of things that we haven't even thought of or conceived of at this point in time. So I'd like to thank you very much for your attention here. And if you have any questions, I'll open up the floor for questions right now, or if you want to try and play with the magnetic writing pad and the magnetic imaging pad here, you're welcome to come up and give that a try. So thank you very much. So any questions? No? If you're too shy to ask questions in the big group, you can also come up and talk to me later on.
Why nano? Why not pico? Is it just because of limits of technology, or?
Well, okay, so the size of the distance between atoms in a material is usually, it's angstroms, so that's like 0.1 nanometers, so that puts a limit on how far you can go. But really why nano is because you start to get interesting properties happening when you have these intermediate collections that aren't quite bulk materials, where the size and the geometry really has an impact on the kinds of properties that you see versus when you're starting to look at individual atoms. So it's based on the fact that you have very different behavior in those size regimes, more so than.
So both technology that you really can't get any lower than the nano? Really...
Well, sure you can, but not with
Not with current technology, right?
Yeah, well, I mean, people do particle physics and they're working with things that have, in some cases, undefined sizes that are much, much smaller. So there's many orders of magnitude in terms of smaller below nano. And certainly atomic is much smaller as well. So.
Curious why nano is such a popular level of dimension as opposed to, say, pico.
It's because of this fact that you have, in a lot of cases, tunable properties that come up in these intermediate size regimes between the atomic and between the bulk. And so you get new material properties that you don't get otherwise. So, yeah. So, anyways, so I think that I'm done. Did you want to?
Any other questions? Okay, Kristen,
Oh, yeah.
thank you very much.
Thank you.
I've always wondered how you manage to read a magnetic field with a magnet without affecting the field.
Basically by choosing your parameters very carefully. Are you talking about hard drives in particular?
Yeah, for instance, that's probably the...
Yeah. So hard drives, you actually use a complicated stack of magnetic materials, but you have bits that are pretty resistant to change.
Okay.
And then you have a head that flies over top.
Right.
And on the side of the head that's closest to your magnetic material, you have what they call a free magnetic layer.
Okay.
And it is relatively easy to rotate as a function of.
Okay. So that one's that one changes a lot.
Yeah, so it's usually about 5 nanometers thick, and it's about maybe 10 nanometers at most from the top of your media.
Okay.
And it flies over top, and so it flips back and forth depending on the magnetic state of the media right beside it. And then there's other magnetic components in the head, but they construct what they call a synthetic antiferromagnet.
Okay.
So what they do is they put together, they have a thicker layer that they use for reading, and they put together 2 layers actually that are together. So the idea is that it cancels out all the stray magnetic fields, so that the idea is to minimize the field that would be seen by the media, so that you don't erase it as you're trying to read it.
Okay. But how do you? Okay. But when you want to read it, what do you do?
That is when you read it. You have
Excuse me. When you want to write to it, what do you do?
Then you construct a big electromagnet. So
Okay. You just jack up the field.
sort of, yeah.
Okay.
They